probably heard me talk about things like coenzymes, NAD, ATP in a few of my past videos, which have been a lot more scientific than what I was doing previously. But even still, you may not exactly understand what I'm really talking about by ATP, NAD, coenzymes, and all that sort of stuff. And that's basically the purpose of this video. I'm going to go through a few examples, mostly ATP and NAD and NADH and all that sort of stuff. But the easiest one to understand and to wrap your head around is 100% adenosine triphosphate, ATP, comprised of 3 phosphate groups, a deoxyribose sugar, and an adenine base. The adenine base and a deoxyribose sugar is essentially part of the structure of your DNA, as well as the phosphate group, but then has 2 more added onto it. It is produced during oxidative phosphorylation, quite a mouthful, but that can also be known as the electron transport chain, which, as the name states, is the transport of electrons during the sort of aerobic respiration process. It can be produced by a few other things, but that often needs an ADP molecule to then produce that ATP after the reaction has been completed and the enzymes use that ADP to produce that ATP. But ATP straight up can only really be produced during the electron transport chain and oxidative phosphorylation. But the reason that ATP is something that's commonly used inside of metabolic reactions is that it is a high energy molecule. It is used in reactions because it has unstable phosphate bonds. The 3 phosphates, the bonds between them are very, very unstable. And obviously this means that an adenosine triphosphate molecule has quite high energy. Adenosine triphosphate is used by the body to produce energy, but it's not a very good long-term sort of plan for your body to use energy. And that's why they have other processes like respiration and stuff, so that your body isn't specifically only relying on ATP to actually produce its energy. Because it's quite a good short-term source of energy because it is so unstable and it is so high energy of a molecule, but it's not a very good long-term solution, as your body only really stores ATP, a specific molecule of ATP, for 3 to 4 seconds at a single time. That's how far some of the chemical reactions in your body are going. It does its thing and then it just goes to do a lot of other things, gets broken down, etc, etc. It's, yeah, the stuff that happens inside of your body, you don't even really notice it, yet it's happening at such an insanely quick rate. But why exactly does ATP and ADP matter when it comes to sort of reactions, producing energy, consuming energy, phosphate groups, etc? Well, the thing is when a lot of molecules have to be metabolized, they often have a phosphate group added onto that molecule, and that takes away a few of the other atoms in that molecule, and then they can sort of take the phosphate group back off, and it turns into a completely different molecule. It's just commonly used in metabolic processes. You probably would have seen in a load of the metabolic videos that I've done in the past, where a molecule will have a load of phosphate groups added on it, and then they'll have them all taken off, and then it will end up turning into a completely different molecule, which is, it's quite an interesting thing how phosphate as a functional group can be used in that way. But as well as that, the molecules themselves, ADP and ATP, are used in the reactions to actually consume or produce energy. The reactions where the product sort of needs a phosphate group added onto it will often have an ATP molecule on the left side and an ADP molecule on the right side, simply because that reaction has taken one of the phosphate groups and added it onto the other reactant, and then you're left with ADP. Because of a few other sort of chemical things, physical things, which I'm not quite sure how to explain really, ATP to ADP ends up using energy from your body. This essentially ends up burning the calories. All the metabolic processes where ATP turns to ADP are calorie burning sort of metabolic processes. Yet the opposite way around, when an ADP it turns into an ATP, if a phosphate group is being taken away, that reaction ends up producing energy, and that happens during a specific process known as glycolysis. While a lot of reactions need the sort of ATP to be sort of on the left side, and the ADP to be on the right side, glycolysis in a few of its reactions has the ADP on the left side and the ATP on the right side, and that means that reaction produces energy, and in the whole process of glycolysis, you end up with 2 net ATP molecules produced, 2 net NADH molecules produced, which I'll go through in a little bit, as well as 2 pyruvate molecules produced. that's just an interesting thing. That is essentially how ATP can be used to produce energy. Now, the second sort of process / molecule that I'm going to talk about is NAD plus and NADH. NAD plus is essentially reduced NADH. Now, reduction in sort of chemistry terms is the gaining of an electron, and an electron has a negative charge, and that's why when NAD plus gains an electron, it gets reduced, and that turns into NADH, which has a completely neutral charge. But the interesting thing is that NADH is the higher energy molecule in a way. I know I talked about ADP and ATP, ATP being a higher energy molecule than ADP, but NADH is technically like a better molecule for your body to have than NAD+. It's an interesting thing, it's because NADH is then used to produce ATP, and ATP is like better than NADH, and so it's sort of like carries on going in a continuous cycle. But as I said before, when I was talking about the sort of net energy gains in the glycolysis process, which I did do a video on, if you are interested in checking that out, it'll probably be like a card or something on the screen. But 2 NADH molecules are produced in the process of glycolysis because when you've got one glucose molecule, it produces 2 pyruvate molecules at like a certain reaction. I think it's step 5 or something where it splits. And the reaction after like step 4, step 5, you end up having 2 NADH molecules produced, one on sort of each side of the branch. And that means that for one glucose molecule, you end up having 2 net NADH molecules produced, which is great for your body because that will then be used in the electron transport chain, the oxidative phosphorylation process, to produce more ATP for your body to use as energy. But as well as NAD plus and NADH, you now have NADP plus and NADPH. I've also mentioned these in a few of my videos, and while it doesn't really come up in glycolysis, I think I mentioned it a little bit in the sort of metabolism of cholesterol video. But NADP plus and NADPH, it's essentially like a level up from NAD plus and NADH. The P in NADP stands for phosphate. A little bit like ATP, the phosphate group means that an NADP plus molecule has a higher energy than an NAD molecule, and that means it's sort of better for the body to have that and be producing that on a regular basis than it would be if it was reducing NAD plus. And again, like the sort of NAD plus process where it turns from NAD plus to NADH and that ends up producing energy, the same thing applies to that. NADP plus turning to NADPH, and it gains an electron and all that sort of stuff, that ends up producing energy, which is just, to be honest, great news for your cells. But a bit like ATP turning to ADP, it can happen the other way around. NADH can turn to NAD+, NADPH can turn into NADP+, and that will end up using energy. Just exactly the same as how ATP turning to ADP uses energy, it's just the exact same way around with NADPH turning to NADP+, when NADPH is on the left side and NADP+ is on the right side, that will end up using energy. And just like how ATP to ADP was a calorie burner, that is also a calorie burning process. In terms of sort of like the tier list for what your body wants to use to produce energy, NAD plus is at like the bottom of the tier list, then it's NADP plus, then it's NADH, then it's NADPH plus, which is like the creme de la creme for your mitochondria to use for certain cellular processes which end up producing energy. But the main uses of these molecules are glycolysis, respiration, and the Krebs cycle. I've gone through glycolysis. I may go through the Krebs cycle in another video. I've gone through glycolysis. I haven't quite gone through respiration yet, although it is quite a basic sort of thing that happens inside of your body. And I haven't gone through the Krebs cycle yet, which I will do in the future. But they all sort of kind of interlink and interconnect in a way, which is just very interesting. And that's kind of another reason that science interests me quite a lot, because everything sort of does seem to connect in a really nice way, which makes you sort of be really grateful for how the processes work in your body. But again, I hope you enjoy this video, and I also recommend subscribing because I love this community of young tribal people who are willing to improve themselves so much more than you already have. And good luck.